Okay. So we continue our work. The program which we are discussing now is about matching of contours and finding the distance between two of them. So for this purpose, you have to read a file which includes a template image. And at the same time, you need also to read from a file the target image. Then we use IMAQ Extract Contour for both cases in order to get as the output the template contour and the target contour at the output. Or in other ways, the source template points and the relative also target points. So the source template points are shown here, as you see, as an array of clusters. Yeah. Here also, the target points are also shown as an array of clusters. Here it is only not minimized, not as an icon. Now I'll show as an icon. So it is like an icon. To make or to find the distance between both contours, or the contour which is realized by the template points and the contour realized by the original or target image points, we use IMAQ Compute Contour Distances function here. And in order for this function to work properly, you have to define the order of the kernel, and we have to learn the contour pattern. The contour pattern is learned by a specific function also called IMAQ Learn Contour Pattern, which feeds its information as an input to the compute contour distances function. These functions exist here in IMAQ Vision. This is machine vision. You click it and you will find here at the searching IMAQ Learn Pattern. This is IMAQ Learn Pattern 6, which is here, which we use it here. And also concerning the IMAQ Compute Contour Distance or distances, which finds the distances, well, I think it is with the contour here, IMAQ Compute Contours, as you see here. This is the function which I am talking about, which has two inputs. One of them is the target contour image, and the other input is the template contour image. And of course, as the output, you will get here an array. Practically, this is an array of clusters as the output. It is here, as you see. It is the array which includes the clusters. This is all, this box is a cluster. This other box down is another cluster, and so on. And each cluster contains 2 points. One of them is the target point, and the other one is the relative template point. And it gives to you the coordinates of both points, the target point coordinate and the template point coordinate, x and y, x and y. The program uses these coordinates to calculate the distance between the target trajectory or target curve and the template curve. This distance here for this point, which is the error or which is the difference, is equal to 0.61 pixel, less than 1 pixel. If you go to the other 2 points, the second 2 points, you will find the distance 0.7 pixel. If you go to the third one, you will find another value. So at every specific 2 points, you find a distance between them, which represents some kind of error or mismatch between both curves. How the distance is found here, it is easy. You have to find the difference between x and x and the difference between y and y, square the differences, both differences, x minus x squared, y minus y squared. You add squared values and find the square root of them. You will get this value. Now, in order to judge about the quality and the difference and the value of the error, normally you compare this distance with an allowable threshold value of deviation. If we want to work in the range of 1 pixel, for example, so this distance can be more than 1 pixel. You can put the threshold value 2 pixels or 3 pixels or 5 pixels. If you want to work with an accuracy which is in sub-pixel range, as it is here, in this case, you write the deviation, maximum deviation or error value or distance equal to 1 pixel. This is shown here, as you see, for the template contour curvature and the target contour curvature. As you see, these deviations for each of them, and it is as a maximum shown here about 0.6%. Really, it is very small, less than 1 pixel. And if you want to make it relative to 1 pixel, you put here 1, and here you put 1. It is already, so it is seen that it is about half a pixel, not more. This is the reference value, of course, which we want to use. And this value, of course, must be included in the program and compared for every point with the reference, and you can have information whether it is higher or lower than the threshold value, and you can use this value to judge about the degree of matching between the 2 contours. Yes, this is the main target, of course, which we are aiming at. If we go back to the, I'm sorry, here I have noted for you some notes to remember. For contours matching, the distance between points must be very small and less than a threshold value. Threshold value, not here. T. Threshold value. When contours mismatch, you will get a message illustrating that. You compare the distance for every point with the threshold value. And if it is greater than the threshold value, you get this message. Contours may be aligned as shown below in the figure here, or rotated by an angle relative to each other. So you can, here it is, one of them is rotated relative to the other one. In this case, in match mode, rotation is enabled. There is a match mode box here, match mode box. You have to enable the rotation mode. Distance between contours is the distance between each two related points and is calculated as I explained to you. Template contour curvature and target contour curvature show coincidence and good matching between both, as you see in this figure here. The last note, when the template dimensions were changed, the basic template reference template dimensions of this figure here are 640 by 480 pixels. I tried to change them a little, but to keep coincidence and matching existing. So I deviated it very little. Instead of 680, I took 480, I took 485. And here, in the third case, I took 645 instead of 640, so that there will be mismatch between them or distance between them. For the first 3 points, which are shown here, the mismatch was about 0.3%, as you see here, about 50%, and 0.5%. Here about also 0.48%, which is calculated as I told you. Here the distance these values are different, not for these values now. These distances are for 640 only. I have to change the scale. I am very sorry. For discomfort. Well, I think this is the target of this example, to show you that if we have a template and we have an original system, for each of them we can derive a contour. Contours, of course, should be near to each other to match. And if we want to have an idea about the matching degree, we make use of the distance or the error value between every relative 2 points here. Yes, and also we can make use of this error, which is the distance, and compare it with a threshold value to decide whether this mismatch is unacceptable or this match is acceptable. Okay, this is all about this example. So we move to another example. Okay, this example is not completely new for you. You know about it, but I prefer to give it to you as a special standard program because you may need it very frequently in practical life. It is how to extract template from an image. From an image, this is standard. Or what you need is to define the area of interest for you and to extract, yes, a template, which could be used for matching purposes, for comparison basis. And you use this template to introduce it to a matching function in general. So as you see here, we have a file which we read as usual. Here we have an overlay clearing overlay if there was an overlaid information on the image. Now it is not existing. Then we define the region of interest and select the required tool. Here we are selecting rectangle, but we can select any of these items included there. In general, the rectangle is the most common. And the region of interest, as it is a rectangle, is fed as an input to the extract function here. Of course, the extract function requires a memory buffer. So this is the memory buffer allocated for the extracted part of the image. And this will be fed to IMAQ Learn Pattern 6, which I showed you before. So this function will read the extracted image and will give you opportunity to have a picture of the template and related information to the template. The related information, as you see here, they are a cluster, as a cluster. It is called template report. Also, I have saved the template in a specific file because very often when you extract an image, a template, you need to use it in future for matching purposes. Really, I have established a folder in the computer, and I keep there all the extracted templates, which I expected to reuse it in the future. So this is just a write file. Write image write file. And in this file path, I describe where to put the images. It is called, the image itself here, in this case, is called a screw PNG. And it is saved in LabVIEW IMAQ processing folder. But really, I used to put it in another more specific folder here, which is called used templates. So let me here go back to the window. Used okay. Pro CING processing slash used templates slash and the name. I have given it a name used screw PNG, no problem. Let it be there. Now, the image which we are going to work with is called parts. This is an image of lab view. I will show you where it is. And from this image, I will extract yes, parts 00 PNG image. So parts is the name of a folder, and parts 00.png is the name of a file there. How I go there? Okay, I can show you to the disk C, users, public, and public documents. Now I am at national. Here is the Vision folder. And in the Vision folder, there are examples. And for these examples, there are images. And from these images, I select the one what I want. It was called parts, as I told you, FGHOP parts. Here is parts. This is the folder which includes different parts. And here, each of these images includes a part. So I selected, for example, part 0, part 0. Okay. Oh, I don't need it there. It is already selected for me. So now it is here, it is transferred to the Vision Assistant. I do not need to work with it now. I shall work with the program which I have written. So I go back to my case. Here it is 00 PNG. Now, if I run the program, I'll get the page, and I select the element which I want. Suppose I want this element, as it is the case, and I say OK, and it is existing here. And it will be saved in this file. If I go to image processing, let me see. This is the desktop image processing. Here it is. And in image processing, I have a folder called used templates. Using so and so here, used templates. If I open it, I will find there the images which I saved. This is it was called previously screw. Now I may give it a name used screw. So now it is a template which is saved in a specific folder. As I told you really, this is a very interesting example because it is used very frequently in life. So I try to give it a specific interest. Okay, we continue our work. We were here at 25, extract template from an image. The second example is also very interesting, with a title IMAQ Extract Curves example. Let us go through it. To understand better, I prefer to go to the block diagram at first to have an idea about it. So where is this function? It is this one, IMAQ Extract Curves. If you face such an example here and you do not know from where to how to find this one, and you do not have an idea about it, just go to the help and you will find that this function, or VI, exists at the analysis palette. There is a palette called analysis and night vision development model analysis. So if we go back to our main palette here, we have to go to analysis, image processing. I think it is there. This is the analysis. I open it. Here it is under hand. IMAQ Extract Curves.vi. This is this function. Okay. I have written two words for it. It finds the curves in the image. So practically, in a way or another, it gives you an information about all the points which represent a curve, which represents the edges of a function, of an image. So if you go and see, for example, this bracket, we are talking about these edges, the external edges, and that this function gives you an idea to have the coordinates of all these points which exist in this image, which is very similar to contour function. Okay. In order for it to work, all we need is to give the input here, image, which you read from a source, and you directly will have two interesting ports. The port here is curve parameters, where you are supposed to modify some of the values which are given here. Some of the values are as indicators. If such an image is a closed contour, it gives you here, it lights, it is put on and gives you an idea that it is closed, for example. You have a recommended value for thresholding the image, which means that this function makes thresholding internally. And also it includes a filter and gives you options to work with as a normal or as a contour tracing. Really, we are interested within contour tracing. So it is contour. The other values, normally you do not change that much. Okay, so we go back. While finishing with curve settings, you will get the output here. It is called curves. I have managed to work with curves for realizing specific purposes. First of all, through this sequence, I managed to get the image as the output for a period of time which is equal to 100 seconds, which means 1.5 minutes, approximately. Then it is put off. Of course, I can work without it, but I did not want to keep it running all the time. And I took the array here of clusters and indexed this array, and through the unbundle function, I wanted to reach, sorry, I want to write for you only, unbundle by name. I wanted to reach the points. Here, if you open it, you can get other information which you do not need. So I used only the points. And these points now are as an array. And this array here, the array of clusters, the symbol is specifically, I put it to show you. And I fed it to another interesting function, which is IMAQ polygon area. What is this polygon area? If you go to the machine vision functions, you will find analytic geometry functions, and one of them is IMAQ polygon area, this function. As you see, this function includes a configuration with different vertices. Each vertex is a point with a given coordinate. This algorithm could be used to find the area which encloses all these vertices. The minimal number of vertices required is 3. Of course, here we have a lot of points. So they are sufficient to use this function in order to find the area, this area, which is included by the contour. So when I run, the area now is 0. If I run the program, I get the area in pixels, which is 54,382 pixels and a half, which represents the areas enclosed within this contour. One thing you need here to think about that these holes, when this hole and this hole are not included. So you need to find the areas of these two holes in specific functions. I may show you it if there is time for this. Of course, I have given you an option. You can refer to classification folder and find an image called gear, and there you can find its image, its area. Let us go and find it, for example. So where it is in classification. So we'll go to images. Here is images. We'll go to classification. Here it is, classification. And here what we get, gear, motor, gear. Here gear, we have gear 00, we have gear 01. Any of them. We took gear 01, and if we run the program, now we have its contour, and now we also have an idea about the area within this contour, which is about 2,166 pixels, and so on. So I think the idea is clear how to use this function, and I recommend you, of course, to make use of it. It is very useful in real life. And I do not think that there is other important things to use here. The XY graph here is the graph which represents the image itself. And that's it. So it's okay. We're finished. .26 .2. I think I have given it a special interest here. Maybe let us look at it before going to another one. Maybe I'm repeating myself or not, I am not sure. Oh no, it is not a repetition. Really, what I have done here, what do we have here? As you see, the function which we are working with is we want to find the area of a specific image surrounded by a contour. Here we do not have the function which I told you about in the previous example, neither we are using the contour function. This is another new third function. Let me give you its name and go and show you where it is. Should have a name. It is called IMAQ here. I don't know why, really, I have noticed that, but it is detailed. I will show you where it is. Here it is. It is called IMAQ Get Points on Contour. Get points means X and Y coordinates. Each point is described through X and Y coordinates. And because we have many X and Y, X's and Y's, so we have an array. So this function gives you an array which includes also the coordinates of the points. Get points on contour. Let us go and see if it is given this name or IMAQ in the help. Sorry. Let us go at the help first and see what is there. It is called Get Points on Contour.vi. And this function differs from the previous one, which we have looked at just now, that it has an input image, but this input image is edge image. So it must be thresholded. The image here must be externally thresholded and is not thresholded within this function as we have seen in the previous example. In the previous example, when you set the parameters, there is a specific setting for the threshold, which was given number 75, and you have the choice to increase it or decrease it to have a better thresholding result. In this example, you need to threshold the image before feeding the image to this function, which is important. Okay, now we know a little bit. At the output, of course, we get the number of segments which we have, and we have also the information regarding the segments which we have, and this information could be utilized also in order to find the area of a given image. This is the target of this example which I am showing you. So here is our function and leads an image which is thresholded. Really, the image itself begins from the file here. And this file is red, as you see. The file is red, and this is the output image. This, as you see, input here to IMAQ edge detector or IMAQ edge detection function. The read file which I am dealing with now is this read file, not this one. This one is isolated and kept alone for other purposes. So the output image is this one, and this one will be thresholded. Here it is at the given of the edge detector, as you see. And at the output here, I got the thresholded image. I inversed this image, and the inversed image is subtracted from a copy of the image so that I can carry out the calculation of the area. Why? Because when you have the sensitivities of the image, really you get the area which is surrounding the whole image, not only included within the contours. And I want only the area within the contours. So I inverse the image and subtracted that part which is white around the image in order to keep the area which is of interest for me here. Now this area, by using the, again, unbundle function, I used the information of the segments, and I took the points which of interest, and at the end, I manipulated them to have here an array of segments which calculates the area of the same battery clamp. This is really done specifically for comparison purposes. So, if you go to the front panel here, this is the bracket of the battery or battery clamp of interest. These white areas which were outside the image were subtracted from the whole area, this one, so that I can work with these black areas. And when we calculated the area, it was found 54,591 pixels. In the previous example, it was about, I have forgotten it, but I think it is very, very close to that. I think it is this one. You see? Where is the area? Here it is. Here it is. Oh no, this was the area of a small circle here. Let me see the previous one. I'm sorry. The previous example, maybe 26, when no, it is 26 one. Let's see. Let me see. Really, I made it. No, this is different image. This is sub-image, not needed. Let me go back again and have a look at it. We worked with the edge detection. We worked with 26 extract curves example. Find area. This is which we are working on now. It is either 26 or 26-1. Let me see again, 26-1, maybe somewhere it is given. Anyhow, let me run it for you and see. Here it is. Here the contour, it is 54,047. 54,000.47 pixels. Now, in our example, which I am discussing with you by using the other function, which is 26 dot 2, it is 54, as you see, 591. The difference is, let me say, about 550. 550 pixels. 550 pixels. If you divide by 54, 591, you will get an error is equal to 1%. Dot 1, which is really negligible and means that both functions work and give the same result. This is the target of my talk with you. Okay, now we have finished with 26-2. Here is another example. I'll give you an idea about it, and then we will finish today. 27. Here we have an image. We are interested with a specific area, but this area of interest, we want to draw it on the picture, and it should have a circular shape. If we go to the block diagram, the idea is simple, but I wanted to acknowledge you with it because when you go to the front panel and right-click and go to Vision, here you find Machine Vision Controls. Machine Vision Controls gives you facility to manipulate an IMAQ circle or IMAQ rectangle or IMAQ line or IMAQ point. IMAQ coordinate is specific if you want to change the coordinates. Our target today to show you how IMAQ circle works, so you just click it and put it at the front panel like this. Here you have to fill the values of interest for you, which is the coordinates of the center, X and Y, and the radius of the circle which you need, and if the circle has a thickness, the outer perimeter and the input perimeter locations, which is the outer, defined by the outer radius and the internal radius. Here inner radius, here outer radius. So as you see, this control now, here I don't need it. No, okay, let me show you. When I go to the block diagram from here, it is represented as you see here. And the interesting thing here is it is given as a cluster. So it is directly matchable with convert annulus to region of interest. So the region of interest for us now is an annulus or circle, which is fed to IMAQ overlay this region of interest on the photo, on the image. So we overlay this region of interest, which is represented as a circle, on the image. Of course, with the given color as described here, and the given parameters which are described here. So if you go back and run the program, you will have this. Oh, okay. You will have this image. If you change, of course, you can change any figure you want. Suppose we want to go to another. Let us try to do this girl, for example. This is PNG. And if we run the program, we got it and we got this circle. Now let us change these circles. For how to change them, because I have to know about the image itself. If I want to encircle this eye here, so I know this coordinates of this world is 214 by 146. So I write here 214 by 146. This is the coordinates of the point here, for example. And I need this point maybe very close to it here, down. 258, 200. I don't need another, no, sir. I need only the eye. So I need only one point here so that to be concentric. So I need the coordinates of the eye. 236 by 164. 236 by 164. And the radius, let it be the same size as here, 30. I can make it larger. If I run the program now, you see, it is centered in the eye with the same radius. Of course, you can make this 20 or 10 to be more closer to the eye as you want. Okay, with these examples, I finish our discussion today. I am sorry that my voice is not that good, but I think that what I wanted to tell you, I have told you. Wishing you the best, and goodbye.